capacitors.
And I guess also inductors.
Yeah. Yeah. No, I understand. Let's see. An uncharged 0.2 microfarad capacitor is driven by a triangular current pulse. The current pulse is described by this. Derive the expressions for the capacitor voltage, power, and energy for each of the time intervals needed to describe the current. So I'm going to do, I'm going to start with just the voltage, and I may or may not do the others. So let's remember our expression for voltage from current. It is 1 over c, the integral from the time that we start to t of I dt plus the voltage at the time that we start. And remember, these are not going to give us numbers, these are going to give us functions because we're trying to get a function of time. So for less than 0, so for time less than 0, the integral of 0 is just 0, so v will equal 0. It was not charged at negative infinity, so we don't have to worry about that. Okay, so now let's look at from t equals 0 to t equals 20 times 10 to the negative 6 seconds. So that would be 1 over the capacitance, which is 0.2 microfarads, and 1 over 0.2 microfarads is 5 times 10 to the 6. So I have 5 times 10 to the 6 times the integral from 0 to t, because I'm starting at 0, of 5,000 t dt plus the voltage at my starting time, which was 0. And it says that I started uncharged. So this v of 0 is 0, but I put it in there because sometimes it's not. And notice this, this all goes together, and then this is added on outside everything else. So this is now 5 times 10 to the negative 6 times 2,500 t squared from 0 to t. And I'm not putting in my ending time because that would give me, if I put in this number, that would tell me what the voltage was at 20 microseconds, but that's not what the question is asking. It's asking what is it as a function of time during that time interval. And so then I get 12.5 times, this is 5 times 10 to the 6, positive 6. So then this is 12.5 times 10 to the 9th t squared volts. Okay, so that is our first time period. Now let's look at our second time period, which is from 20 to 40 microseconds. It is. So 20 less than t less than 40 microseconds. So this will be the integral from our starting time, which is 20 times 10 to the negative 6, to t of 0.2 minus 5,000 t dt times 1 over the capacitance, which is 5 times 10 to the 6, plus the voltage at our starting time, so our voltage at 20 microseconds. So then I get 5 times 10 to the 6, 0.2 t minus 2500 t squared from 20 times 10 to the negative 6 to t plus the voltage at 20 microseconds. So when I plug t in, that's easy. So it's 5 times 10 to the 6, 0.2 t minus 2500 t squared. And then minus 5 times 10 to the 6, 0.2 times 20 times 10 to the negative 6 minus 2500 times 20 times 10 to the negative 6 squared plus the voltage at 20 microseconds. So now if I distribute this 5 million, I get here. If I distribute the 5 million, I get 1 million t minus 12.5 times 10 to the 9th t squared. And then I don't know what this is. It's 15. So minus 15 plus the voltage at 20 microseconds. Now, how am I going to get the voltage at 20 microseconds?
Plug it in.
Into what? The first one. So let's see, I had my answer to my first one because this was good from 0 to 20 microseconds, and we know that the voltage can't change instantaneously. So whatever it was here is what it has to be there as well. And so if I plug in 20 microseconds there, I get 5. So this then becomes 10 to the 6t minus 12.5 times 10 to the 9th t squared minus 15 plus 5 is minus 10 volts. Okay, now for greater than 40 microseconds, the voltage will equal 1 over the capacitance, 40 microseconds times t, times our current, dt, plus the voltage at 40 microseconds. Well, our current for greater than 40 microseconds is 0. So this whole part will be 0, but our voltage is not 0. Our voltage is whatever it was at 40 microseconds. And if I plug 40 into that, I get 10. And so our voltage looks like 12.5 times 10 to the, 0 for t less than 0, 12.5 times 10 to the 9th t squared for t between 0 and 20 microseconds, and then 10 to the 6th t minus 12.5 t, this was squared. 12.5 times 10 to the 9th t squared minus 10 for t between 20 and 40 microseconds. And 10 for t greater than 40 microseconds volts. Okay, so that was so much fun. I know that you will want to do the power and the energy, and you don't really. So that's just algebra. So I'm going to skip that part. You can do, yep, you can do that at home for fun. So speaking of fun and not fun, this one we have the voltage, and you're supposed to find the current. And this one is a product rule, and it is a lot of math, a lot of numbers. So I'm going to come back to this one if I have time, or maybe just post a recording from a previous year, because it's just not, I don't want to do that. I'd rather do this one. This one is more fun. So this one is to find the equivalent capacitance with respect to the terminals AB for the circuit shown here. And I feel fairly certain on your next test, which is when? Do y'all know yet?
I think it's next week on
I
Friday.
think it's next Friday, yeah.
Oh,
She almost always has a find an equivalent capacitance or inductance. So you just have to remember how they add. So capacitors add the opposite of resistors. So let's take a look at this first one. Find the equivalent capacitance with respect to the terminals AB for the circuits shown here. Okay, so when we're looking for the equivalent capacitance, we are not concerned with these voltage sources here. Oh, sorry, there are no voltage sources. No, it's not a voltage source. It's just showing what the voltage is across that capacitor. These are all capacitors. So that's one way to show a capacitor. So you have this way with the two straight lines. The other way is with one line like that and one line like that, with the plus, the straight line being the positive side. The Circuits 2 instructor likes to do them with the curved line. So starting with these two, those are in series, so that means they add like resistors in parallel. So our equivalent capacitance for those two is 48 times 24 over 48 plus 24 nanofarads, which is 16 nanofarads. So now I have This is 16 nanofarads, and this one in the middle is 4 nanofarads. So now I have capacitors in parallel, which add like resistors in series, so we can just add those together. So now I have these two added together, these two added together are 20 nanofarads, and they are in parallel with 8 nanofarads, so you can put those together and get 28. And then I have,
I thought that 30 nanofarads at the bottom was things.
because, yeah, that'd be useful if I remembered to draw it in. So hold on, where is it? It is right here. So yes, that would definitely mess things up. So hold on. That one would be right here, 30 nanofarads. Yeah, so we have to add the 20 and the 30 in series. So that's 20 times 30 over 20 plus 30. So that is 600 over 50. 12? Okay. We'll see when we get to the end. Okay. Now I have an 8 and a 12 in parallel, so I can add those together and get 20 nanofarads. And then at top I had 20 and I had 10. Oh, and this will work out not so bad, because I know that 2 resistors in parallel that have the same resistance, the equivalent resistance is half. So if I do this 20 and this 20 together, the equivalent capacitance there is 10. And then now I have a 10 and a 10 in series, and so that equivalent capacitance will be 5 nanofarads. And let's see if that's actually right. And that is actually right. So, okay. All right. So now let's do the second one.
What was the final one you said?
5.
Okay.
Okay, so to start off with, I have a 36, an 18, and a 12 in series. And I don't have anything nice like that last one where I had the 20 and the 20 and the 10. So I'm just going to do 1 over 36 plus 1 over 18 plus 1 over 12. Because you can't do product over sum with 3. You either have to do 2 at a time, or you do it like this, and that gives us 6. So now I also have this 25 and 5 in parallel, so I can add those together and get that to be 30. And now the 24 and the 6 are in parallel, so I can add them together and get 30. And will the equivalent capacitance be a third? Will it be 10? I think it will be, but let me just double check that. I know that the 230s will be, what's that? The 230s will be 15. So then I have a 15 and a 30. And then I would have 15 times 30 over 15 plus 30, which is 450 over 45, which is 10. So our answer would be 10 microfarads. So any questions on that?